It is my pleasure to present our next speakers, Dr. Elizabeth Loudon and Ms. Karen Hughes. They will be presenting preservation technology tools at the College of Architecture. And Elizabeth Loudon earned her doctorate at the Department of Archaeology Institute for Advanced Architectural Studies, University of York. Following a Master of Architecture at Texas Tech University College of Architecture with a focus on historic preservation and a Bachelor of Architecture professional terminal degree at Texas Tech, Dr. Loudon has over 20 years experience teaching at TTU, as well as within the field of historic preservation and cultural resource management. She currently serves as a capacity of Director of the Master of Science in Architecture, specialization in historic preservation program. An extensive career in research and teaching has kept Dr. Loudon at the forefront of scholarly thought in building preservation and conservation. Dr. Loudon's area of expertise include LIDAR, 3D laser scanning, which she gonna demonstrate with Karen Hughes today for us, materials deterioration, high dynamic range photography, large format photography, and mapping, as well as historic structural reports, building assessment reports, archival research, and technical report production. Over 35 projects have been accepted at the Historic American Building Survey, the HABS, and the Historic American Engineering Record, documentation and measure drawings documentation for archival storage within the Library of Congress. Acting as a consultant to both communities and private firms, Dr. Loudon has enjoyed numerous public projects, both in for-profit and as a part of coursework projects with the students. The most noteworthy project has been the opportunity to direct the creation of the first ever measure drawing documentation of the Statue of Liberty for Liberty Island for HABS. Special interest areas are structures of the Stewart development, including ranches, farms, and more specifically, wood deterioration in early West Texas structures. Dr. Loudon currently serves on the Texas Plains Trail Regional Executive Board, following 6 years of service on the Texas Historic Commission State Board of Review for National Register nomination. Wow. So we'll move to Ms. Karen Hughes. Karen Hughes is a training and application specialist with Leica Geosystem High Definition Surveying Division. Ms. Hughes has worked with Leica since 2008, teaching hundreds of students from all backgrounds the hardware and software involved in 3D laser scanning. She has an extensive technical experience in LIDAR, ranging from fieldwork, production, and software. Ms. Hughes received her Master of Conservation Studies from the Department of Archaeology, incorporating the Institute of Advanced Architectural Studies at the University of York, England in 2000. Ms. Hughes is also the NPS Architectural Historian and Preservation Specialist with over 10 years experience in the fields of historic preservation and cultural resources management. Ms. Hughes' area of expertise, including the HABS, the hair and mitigation documentation, measure drawings, material deterioration, LIDAR, high dynamic range photography, and mapping, as well as the planning and execution of cultural resource assessment surveys, archival research, technical report production, Section 106 of NEPA, coordination and consultation, and community outreach. An extensive career in historic building research and writing GIS and map graphics, as well as large format photography and historic district surveys. Ms. Hughes brings a wide range of technical writing and surveying expertise. Over 350 large format photographs in the Library of Congress, prints and photographs division are credited to her. Her most recent preservation-related project is the Booker T. Washington High School Section 106 Mitigation Documentation Project in New Orleans. Ms. Hughes and Dr. Loudon undertook large format black and white photography documentation of HABS and FEMA requirements in January 2012 as a project within their joint private consultation firm. With that, please join me to welcome our two presenters, Dr. Loudon and Ms. Hughes.
think that sounded much grander than it really is. But anyway, thank you, Rima. We appreciate that very much. What we're going to do is pretty much a dog and pony show here. We have included a lot of students in our work that we want to show you, because after all, our purpose here is to teach the students and allow them new skills and to be prepared for a very technical and difficult career in the future practice of architecture. I think in the sense of difficult, in the sense of the changing technology that they have to keep up with, and learning new skills constantly. And as you can see in Peter's work, technology plays a huge role in everything that we have to do, particularly in preservation and especially in architecture as well. So Karen and I are going to show you some of our recently acquired and some other technology that we've had for a while, thanks to a great deal of support from Dean Vernoy and Dr. Hawk and the Vice President for Research, well, at least in September, we suddenly had the opportunity to acquire a new scanner this last year. Of course, we've had one since 1999. We had one of the very early 3D laser scanners. Then that one unfortunately fell down into a Kiva, and they were more worried about the Kiva than our technology, but anyway, as well they should have been. Then we had a second scanner that we've used extensively on the Statue of Liberty and a huge variety of other projects. Along the way, adding other pieces of equipment to our capabilities and trying to keep up a little ahead of all of this. But I distinctly remember Dean Vernoy calling me on the phone saying, can you get a bid? Can you get a PO? And can you get the equipment on campus in about 10 days? And I was like, sure. And I was lying on the highway, or driving on the highway. So I called Karen, I said, who's the salesman for Leica? And she, or I texted her or something anyway. Thank goodness for smartphones now. And so she texted me right back. I made the calls and the emails began flying back and forth. And in some kind of administrative miracle, seriously, you know how the universities are. We had to spend the money, and we were able to acquire our new scanner and get it on campus by, I think, the next Tuesday. I think we got it here in about 5 or 6 days, which was incredible. And then I said, well, you know, it'd be really great if we could get a GPR. Could you please ask the Vice President for Research if he had a few thousand more dollars? And so he did, and we do, and so now we have more new technology to learn and to share with the students. So I'm going to try to go quickly through this. I am the first one to tell you I am not a GPR expert. We got that in September, and my whole life has been planning a symposium most of September. But we have had an opportunity to have some training on the GPR, and I can tell you a bit about it. And then my Master's of Science student, Denise Hensley, is going to show some of the operation to you, just very briefly. But a GPR is used for mapping and measuring, both 3D mapping and two-way mapping, but it simply locates where disturbances or density in the ground are located. It tells us where to start to look, because we're trying to, well, we had a lot of new piping going on in this building, and so apparently they did dig and interrupt some of our ground lines, our piping and electrical lines outside the building, and if only we had been ready and prepared, we could have actually located that piping and electrical conduit for them before they dug. And that's essentially what we expect to be able to do with this. We have ideas about using it for possibly in cemeteries for locating, well, bodies, foundations, under historic sites or where we think there were historic sites. Sammy's already asked me if we could maybe use some of this out to find trails and that sort of thing in the western part of the state. So it's possible, because with the GPR, it is sending waves, radio waves essentially, into the ground, and it only records where the disturbances are. The other part that I will talk to you a little bit about is the thermography camera. We have had that for a little bit longer, it is a temperature sensing essentially. And then after that, Karen is going to do a demonstration and tell us more about the laser scanner and how it works. And then we have some students that are from Preservation Studio. Well, Eric is going to demonstrate that he understands how to, this is sort of midterm review, how they understand how to turn on the laser scanner. And then two students from Preservation Studio, where we recently laser scanned the TXU power plant in Fort Worth. And we are beginning to be able to bring that into Revit, into BIM models, and using all that information on laser cutters and all kinds of things. So we're taking the scanner information and using it more extensively in studios and in design projects. So that's the plan. GPR is a geophysical method that uses radar pulses to image the subsurface. The non-destructive method uses electromagnetic radiation in the microwave band of radio spectrum, and it detects the reflected signals from subsurface structures. GPR can be used on a variety of material types such as rock, soil, ice, freshwater, pavements, and structures. It can detect objects, changes in materials, voids, and cracks. GPR uses high-frequency radio waves and transmits them into the ground. When the wave hits a buried object or a boundary with a different dielectric constants, the receiving antenna records variations in the reflected return signal. So that's a little bit about how the GPR works. It can be used to map a surface. You can see in this example there, it could be something like a pavement, a sidewalk. It's very consistent, it's very smooth. And so we're trying to find any anomalies that are reflected back. And as Denise will show us, essentially the antenna and the receiving unit is rolling along, actually dragging along the ground and transmitting those radio waves. And they're recorded on the computer. It's a small computer at the top, and every few seconds it's bounding back the radio waves, and so you can see the hyperbolic curve there actually tells us there's something there. It doesn't really tell us what is there, but it tells us something is there, and that's a consistent profile of a pipe or some kind of sewer line or that sort of thing. So, here we go. Okay. This shows us a bedrock profile. I thought this was a good example to show where there is a pavement on the top, and then there's fill, and then there's some kind of unusual shape there. So you can see reading a GPR screen is not a very easy thing to do. It takes lots of practice and experience. And the more we see, well, I'm thinking of burying pipes and then seeing if we can find them and recognize them. So just so that we can learn to recognize what we're seeing in the GPR readout. But the red line shows that there is an edge or a bedrock. There's a different density of material there. So if we were digging and we were going to repave that, we would want to know where there was bedrock that we would run into when we were digging. So essentially, it's the first tool of investigation before you dig, sort of like the the power companies say, you know, call before you dig. Well, we say GPR before you dig, so that we don't destroy property or archaeology or perhaps grave sites. So this technology is something that you can see this, it's based on time. It will read out the depth across the bottom, 84.42 feet is where we started. We've traveled 84.421 feet. And so it will tell you as you go along how much distance you've traveled and also the depth there on the right-hand side of this slide. Okay. I'm just not going. Okay. So I think I'll stop just a second with that and let Denise go and run the GPR across the front of the room here just to show you. We have two antennas. We have a 250 megahertz antenna and a 500 megahertz antenna. They are used depending on how deep you want to send the signal and depending on the material. The high frequency is used for shallow depths. This one is the 250 megahertz, so the other one is wider and it has a different wheelbase and we can just switch it out. There's a module in the back of it that we have to move from one antenna to the other, and then you turn it on. It's essentially a small computer there in front of you, and it's quite straightforward to run the software. And so Denise was here on the day we had our training when the salesman brought it to us and demonstrated it. So she got the dubious honor of turning it on and pushing it across the room in front of you. So she's a MS in architecture preservation student. So essentially, would you like to demonstrate how you would, if we wanted to know what was in the ground right here? It's start a new survey, you tell it, that's pretty much what you do. You would traverse across, back and forth, a particular area that you want to, and of course it's reading out here, and then you can see where if there were any anomalies in the ground. So it says, you know, essentially you would say, don't dig here because we think there's something here. So, ta-da.
So it's taking a section, or that's what
it's bouncing radio waves back and recording them, and we'll leave this turned on. Don't turn it off next time. But
will it assemble those multiple traverses into a three-dimensional image?
Yes, you can do that in the software. You export all of this data, and you can see it in 3 dimensions, and you can slice through it. Yes, and you can track where you think a pipe would be. So that's one possibility. I'm sorry, I'm going really fast on this because I'm anxious for you to see more of the laser scanner. Yeah, we're kind of in a limited area of demonstration here.
Elizabeth, years ago they found a camping site in Coronado, 1541 at Florida. They found metal artifacts, old export points and stuff that they've been looking at ceramic shards, which I would guess take that up there. Because I would guess that in that field you could find where all the pots were.
I think it can be tuned to that fine of a tune, but what you're likely to see is just soil disturbance, and maybe in terms of shift, all soil has been disturbed, but you see a change in that shift, and that suggests, especially after you go traverse it 2 directions, and you kind of confirm that yes, this seems to be an area that there's been disturbance, so that would be your first place to carefully do archaeology.
Is there any way to tie survey control to that?
Yes, and that would be a really good thing to do to set up, I mean,
Is it on the system or is somebody to do?
Don't ask me. What I would do would, you know, set the benchmarks so that I knew precisely where I was starting. I would have a site plan, and I would go, the salesman was telling us specifically how the spacing should be so that we could read it out and be efficient with it. And but I do think tying it to GPR and GPS would be a perfect aspect of it. Okay, the next thing I'm quickly going to show you is a thermography camera. We've had this one for a while. I love gadgets. I'll admit it. But this one, both of these, all three of these pieces of equipment, is critical for non-destruction of historic properties, non-destructive techniques. We don't want anything that we do to cause damage. So that's one thing our technology does for us. Many times it can help us understand where, or isolate where the problems are so that we are focusing our attention there. Yes, this is taking your picture. I see lots of, are your noses cold? But they're all dark. But it's pretty amazing. That's not, I didn't focus it. I'm sorry. I can't go back. I can show you that. This will, in a time lapse, it will take photos, and so it takes a bit of adjustment. You focus. There's a little focus button here, and then you can change the scale of your temperature gauges on this. This can also be. This has been used for years. It's with animals. It's so sensitive it can easily do soft tissue. I don't know if I'm probably not far enough away to show you, but it can detect temperature ranges, poor circulation. They've used it in horses for lots of things. You see that there's poor circulation in the legs of the horse, in arms, so that sort of thing. So it's sensitive down to 0.1 centigrade. So it's very sensitive and can be used. It's the same technology that's used in medical detection of any health issues, and of course much less invasive. But what we primarily are going to use it for is building diagnostics. So we're going to use, we can focus this on hot spots in electrical or machines, and it can help you isolate where you need to pay attention, where you need to prevent a fire, that sort of thing. So it's quickly assessing based on temperature problems. And then in buildings, we can see where there's hot spots or where there's a lack of insulation. You can see on the right-hand side, that's the temperature range there. So it's lower than 63 degrees in that dark spot. I was using this in my house last night and I thought, oh, what is that big square black spot on my wall? You know, so that's exactly what you do it for. You walk slowly through and it takes periodic photographs or videos, and it records these temperature sensing situations where you can isolate where you might have an issue, a lack of insulation, or certainly cracks around windows that are allowing too much air infiltration. This is where it's been used on a roof. You can see the top one is IR scan of a roof showing some problem areas, potential problem areas, and then it is drawn to isolate that, and then you can go in and really do further investigations. Rather than look at the whole roof, you're only focusing on certain small areas that clearly have some problems. And then this is a comparison between a photograph and the actual IR investigations, infrared investigations to clarify where we think there's a problem. Then we have some backup data to help us verify that. So, again, primarily for building diagnostics, we can see blocked pipes, we can see where air and heat is escaping from buildings, hot spots in electrical, and this one here is the lower left is missing insulation. So you can see it's a pretty clear picture just simply based on temperature differentiations. And weatherization and auditing buildings is something that we all want to do because we know the cost of energy and electricity. We know that we want to make our buildings more efficient, and we want to isolate where those spots are. And it's the safest, cheapest method currently available for also cutting carbon emissions. So for sustainable issues, we certainly want to be quick and careful with our technology to save energy. So I'll let you play with this later. I'm going to quickly transition over to Karen because she has a lot to tell us about the laser scanner.
All right, well, I'm going to just give you a really brief, wide perspective of scanning because it's a really, really deep topic, and I could spend a lot of time up here with a lot of technical details. So what I've tried to do is really just pare it down to simple terms and give you a really, really brief overview because I realize I'm the last presentation and you're all itching to stand up and stretch your legs. So hopefully it'll be enough to keep your interest for a few minutes. But what we're doing over here with the scanner is we're going to just have the scanner run for the duration of my presentation. And basically, the scanner that we have over there's many different types of scanners. The scanner that's over there is what we call a time-of-flight scanner. So what it does is it sends out a beam of light and it measures the angle and return of that beam back to the instrument. All right, so time-of-flight scanning was one of the very early technologies introduced to the first commercial grade scanners available on the market. Since then, of course, scanners are used across all industries, so right from the micro to the macro, and basically what I'm going to talk to you today about is sort of the type of everyday scanners that we use in terms of engineering architecture. So I'll span from the macro to the micro, but I'm going to avoid industries like working with dental equipment or the really microscopic phases of scanners, because when you get into scanners of that type, you're getting into all kinds of different types of technology. So the three different types of technology that are existing in what we call a terrestrial scanner, which is standing over there, are time-of-flight scanners, and you're going to see the laser beam going around the room. And basically what it's doing is it's mapping your position relative to that instrument over there. And at the end of the scan and the end of my presentation, I'll show you the results of what we get on that scanner. All right, the other kind of scanner technologies that are available now with these terrestrial scanners are what we call phase-based scanners and waveform technology. So there's a whole bunch of progress going on in the scanning industry, and we're really at an exciting time as this technology moves forward. So it's kind of like the development of high-definition TV from black and white. But back in 1999, when we started with the first time-of-flight scanner, the progression over the last 10 years has moved along, but right now we're really at a cusp where things are increasing in speed, and we're going to see you're finally going to see the integration of hardware and software come into play and actually infiltrate all of our industries. And it's going to become a standard, I'm pretty convinced it's going to become a standard data set that we use, not necessarily to measure and not necessarily as a documentation tool, but maybe just as the 3D representation to tie in our thermography, our GPR, our photogrammetry. It's not there to replace, it's just a tool there to augment. All right, so I'm going to get started, and I've decided to kind of read my presentation so I stay on task and stick to the time that I've been allotted, so bear with the reading. So scanning produces a data set of points in space. Each point is measurable and has an XYZ coordinate, and only takes on specific meaning when we interpret and connect the data to the appropriate application. The presentation, titled Connectivity, was developed with the end user in mind. As an end user, I hope to provide some basic information about laser scanning, its diverse applications, and how to connect to practical deliverables. This discussion begins with a brief introduction into laser scanning, highlighting some of the different types of scanning, illustrating some varied professional applications, and showing a few practical deliverables that you can get out from this type of information. So the basic and most important thing is understanding what the tool is capable of and what deliverables are possible is essential for a successful outcome. Collecting the data is only a small component of laser scanning. The post-processing involves understanding the capabilities of the softwares, its possibilities, limitations, and what other programs can be used to aid with the development of the final product. Laser scanners capture, as I said, three-dimensional real-time measurements of an existing environment relative to its current position. The points can be stored in a variety of formats, but common terminology, when we collect points, we refer to that file as a point cloud. So it's basically, we're taking this laser scanner and we're getting a swath of three-dimensional points, which you'll see at the end, and capturing all of you sitting in your current positions. So you better sit still. Therefore, similar to cameras, and this is where educating the public is hard, and I'm speaking to an audience that is very educated in this, but when you go out to the real world and you start talking to people, majority of us in here think in 3 dimensions, but not the majority of the world think in 3 dimensions. And laser scanners are similar to cameras. When you take a picture, you only get what you see. So there's, in this room, we have a lot of voids and a lot of shadows that are inherently blocked because it's a line of sight instrument. So in order to capture and get full coverage, you have to move the instrument around, and it's nearly impossible to get full coverage, no matter what anybody says, because you'd have to raise it and lower it. In this type of scanning, the scanner must remain stable. And that's not the case with all scanning types, as I'll get into in a minute. Another thing that comes off the scanner data is not just a measurable point, but you actually get an intensity value associated with every coordinate value that you collect. And that intensity value is based on the reflectivity of the surface that you're collecting. So therefore, it works like the color spectrum. So if you've got a very bright white surface, you're going to get an excellent return, whereas black tends to absorb the laser. So on dark surfaces like a coal pile, you're going to get limited return. So and that intensity value can also be filtered down and used as a layer of measurement in your analysis as well. So that adds another layer of complexity to scanning. Okay, there are 3 common types of scanning that I'm going to talk about today, and basically I'm going to go over terrestrial scanning, which I've just sort of given you an introduction, and that's a example of a terrestrial scanner. I'm also going to give you a brief overview of mobile mapping, which means attaching one of those instruments to a car and driving down the highway at 60 to 90 miles an hour and collecting the same amount of information. All right, and I'm also going to briefly touch on airborne lidar. All right, so putting the same kind of, not exactly the same, and it's a lot more complex, and I'll get into a little bit of it, but basically attaching a scanner to an airplane and doing aerial lidar and flying over canopies or vegetation or over the Nile and calculating the topography of the Earth. And you can go online and obviously download lidar data of almost every aspect of the world. It's all been flown, and they use this a lot in surveillance and other aspects. So it has a lot of diverse applications. All right, and then I'm going to go over and show you some of the, I've chosen 5 or 6 different professions to give you a wide range of applications and how it might sort of relate to different people in the room and how LiDAR can be used. And in those applications are just a selection of a few deliverables to show you the broad range of things that you can actually get out of this type of data set. All right, so just a little bit brief to go over terrestrial scanning. So I've kind of explained basically what terrestrial scanning is, but this picture shows a picture of the TXU power plant that we recently scanned, and Elizabeth mentioned a little bit about it. But we basically scanned the power plant in 2 days. The power plant consists of over 47,000 square feet, and we were able to do it in 2 field days, and they weren't long field days. We were out probably maybe 7 hours each day and teaching students how to use it with 2 units. This particular unit is actually collecting 50,000 points per second as it spins around. We have scanners on the market now that are closer range scanners that will collect 1 million points per second. So it's basically a total station on steroids. So if you're familiar with a total station, the old traditional method that surveyors would go out and set up their total station and mark points along the roadway to be able to map the roadway. A good surveyor today can go out to the field and collect anywhere between 800 and 1,000 points per day. So this instrument here is you can just do the multiplication. You just can't keep up to it. So it doesn't eliminate the need for total stations, but it definitely is a tool that surveyors have converted over to because it augments their workflow tremendously. Okay, so I'm just going to derivate from my presentation for a minute to show you, I'm going to show you the point cloud from the TXU power plant. Now this is not the entire point cloud. This is just the outside of the power plant. Okay, and I'm using a beta copy of software right now, and so it's not moving as well as it normally does. And you'll notice, and I'll stop moving in a minute because you have to wait for the computer to regenerate the point cloud. Now the real problem with scanning these days is the hardware development is increasing at tremendous rates. There's a lot of R&D worldwide going into instruments and laser scanning. But the problem is, how do we as users handle the data management? And how do we build computers to handle data sets that are collecting 1 million points per second? You know, it becomes a really hard problem, and the bottleneck comes down to computers. So you've got to invest in good computers with solid state drives to be able to handle this much information. We have other tools that we can do to be able to make it, manipulate it, and maneuverable. But as you can see, the nice thing is you can move the point cloud around and certainly create and get a good idea of space. And every point in that point cloud is measurable. And I'm not going to go into it too deeply because the students are going to show you what they've done with it, how they've taken the registered point cloud from here and chopped it up into pieces to get what they need at in terms of their sections, their elevations, and basically they've developed a full 3D model in BIM from the scan data. So they're going to explain a little bit about that at the end of the presentation. But I wanted to show you, just give you an idea of what that deliverable looked like. And this isn't the entire point cloud. Then again, this is just the exterior. And in areas that you're seeing through the point cloud means it's just area that we didn't capture.
What's the distance? Like I noticed it runs out on the left in the parking garage up there. What's
The range of this scanner will scan up to approximately 400 feet with reliable, measurable data, but it'll actually get returns of 900 feet. But the points out at 900 feet aren't really, they're not measurable.
How many locations do you remember on the outside?
I think we set up around 20 locations around the outside and about 25 inside.
In
So
one day? 20 locations?
20 on one day on the outside, and then we spent the next day on the inside. But again, I just wanted to give you an idea. And after the presentation, you're welcome to come up and play with this and have a look at it. And I've got other data sets if you're interested in seeing more LiDAR data sets. Okay, so I just wanted to just give you an idea of what I'm referring to in terms of three-dimensional object. Okay, so another intriguing thing is this thing called mobile mapping. And mobile mapping's been around a very long time. It's been around, I mean, a long time in terms of scanning perspective. It's been around for 10 years. So terrestrial scanning and mobile scanning are two parallels that are developing at their own rate on different tangents. So mobile mapping has significant advantages over terrestrial scanning because it increases the speed of data acquisition, and it records the points in geo-referenced coordinate system. It's also very efficient, and the productivity of it obviously outweighs terrestrial scanning. The speed of data capture occurs at the average driving speed on the roads and is not a function of the complexity of the surrounding environment. Mobile mapping utilizes laser scannings, global positioning system, or GPS, and inertia measurement units to calculate the position and orientation of a laser beam as it hits an object from a moving vehicle. Mobile mapping is only limited by traffic and speed limits. Also, due to the high resolution and precision of the sensors, the accuracy of the data can be verified very quickly. It's actually verified through all the different mechanisms, and it's not just the scanning, it's talking about the movement and the velocity and the inertia as well. So as the data is captured, it's also verified as it is collected. These systems offer tremendous versatility as they can be mounted on almost any type of vehicle, even a boat or a train. In the UK, for instance, as one example, they mount the scanners on a rail car, and they've mapped all of their train tracks for R&D or future expansion and whatnot. Again, they can be mounted on boats, etc., for transportation and collect thousands of data points. They did a recent survey of the city of Istanbul with mobile mapping. And they just drove around and basically captured the majority of the city with the mobile mapping. The problem with the mobile mapping, though, is that when you drive around, you're obviously going to miss voids. And so what they've done in certain aspects of the city is taken the terrestrial scanner, and because it's already georeferenced, they've set up the terrestrial scanner and they've started to fill in pockets of areas that they can't get to via a vehicle. So it definitely offers a good way to get overall coverage, and then you can go in and fill in with terrestrial LiDAR. And the real main draw to mobile mapping is also the speed of acquisition. It's very easy and fast to do. Airborne Lidar is another type of LiDAR that's used extensively. It's an active sensory system that uses laser light to measure distances. The system is mounted on an airborne device that quickly measures distances between the sensor on the airborne device and points on the ground to collect and generate highly accurate elevation data. Airborne LiDAR systems rely on a GPS and also on an inertial reference system. And instead of getting into the actual detail of how, it's a very complicated system, how that all works, but just to give you an overview of what they're actually doing. Some of the typical LiDAR, airborne LiDAR applications include topographic mapping, digital elevation maps, forestry, flood mapping, coastal studies, corridor studies, urban modeling, and disaster response. And they can take scanning from the macro and do a coverage on top and go right down to the coastline and map the coastline with terrestrial scanning as well and fill that in and get a full comprehensive scanning. They can also take sonar, which is a different type of technology, and they can map the LiDAR to the sonar. So I've seen the integration of airborne LiDAR, terrestrial LiDAR, and then sonar to get the whole underground topography of what's going on along coastlines and whatnot. And this applies to architecture, of course, and fortifications, and also buildings near the coast as well. So again, it has more applications than just mapping what's there. All right, and so just some brief overall applications in different professions to give you a good overview. And I picked these just because I think they're of some interest to the people in this audience. So the first one I'm going to go over is some of the applications and something that's kind of near and dear to all of us in the room, and that's architecture and historic preservation. So instead of going and reading through this list, I just want you to quickly peruse the list that I put up there. And again, this is just a summation of some of the applications. It certainly doesn't incorporate everything that you can do with this instrument, but it gives you a good idea of how we can apply this technology. Now, the drawing in the background was done of a historic grain elevator in Brownwood. So the entire structure of the grain elevator, all that isometric drawing came from the scan data. And we were able to even get down right to the joint connections and show the nuts and bolts. And that's all in a set of drawings that we submitted to HABS for the documentation. All right, this is a scan that we took at the Union Terminal Station in the Art Deco building in Cincinnati, and I just included it because it was a really neat place to scan in it. And I'm just going to show you some of the scan data. I don't have it all put together, but I'm just going to derivate for a second and show you some of the scan data from there. So what we're looking at here is what we call a key plan. It's just basically a site map of the scan data, and I've stitched 4 of the positions together. And what I can do in here is I can double click on one of these triangles, and what I can do is I can open up a menu, and what I'm going to do is it'll take a minute to load, and it's just due to being connected to a projector and using a beta version of software. But as I turn it around and as it loads, basically what I'm doing is I'm looking out through the perspective of the scanner. But you can see all the millions of data points filling in, and all that's filling in are all the data points. So you can actually see there's points there, spaces between the points, and that's points filling in. So you can begin to understand what the density is of the spacing between those points. And you're able to see it looking realistic, because what happens is not all scanners, but this particular scanner has a 5-megapixel camera in it. And so when we go through what we call the import process of taking the data off the instrument, we're able to because the photo is taken in a dome, it takes 260 hexagonal images inside a dome. And what happens is during the process of getting the data off the computer onto the laptop, it takes each point and goes out and finds the pixel relative to that pick point and burns the pixel of the photograph onto the point. And so when we turn on what we call colors from the point cloud, we get a photorealistic view of what we're scanning. Now the only difference is if you, the scanning and the image take place separately. So if you scan this room and then you take the photograph and you've happened to move, you're going to have a parallax between your photo and your scan data. So, you know, there are some mysteries of, you've got to make sure everything is stationary when you do it if you want the result. But in this case, for this example, we're only scanning because the camera in this particular scanner doesn't have a bright enough aperture to be able to let in enough light in this dark scenario to be able to do a good photograph. So when we finish that scan, I'll show you what raw scan data looks like. We call that an intensity map. So when we look at the raw scan data, we're seeing the colors of that reflectivity I mentioned earlier when I introduced terrestrial scanning. All right. You can also, for scanners that don't have cameras, or if you have low lighting situations, you can also mount cameras and take your own external photographs using any type of camera. You just need to be able to process, you have to have enough overlapping data in the focal length of the lens to be able to process it into a dome. And then what we do is we do what we call cube mapping, and we make cubes and then we texture map that cube into Cyclone. You can also go as far as to do HDR, so you can take photos at different lighting. What that means is you can take photos at a variety of lighting exposures, and then you can process those images down to an ideal lighting situation that maps what you need to do, and then you can import that into Cyclone. Applications that we've done that in is when we've done a lot of cave scans and it's really dark and just can't get a good image with the scanner. We've taken in external cameras, mounted them at the same height of the instrument or data capture, and then HDR'd them and then texture mapped them. All right, so there's lots of flexibility in terms of what you can do. So I just wanted to just give you that. And again, afterwards, I can show you more of the images. This is a pretty neat point cloud. And also what's interesting about that is when I had that location opened up, the nice thing about this interactive site map is it shows me the direction I'm facing in this menu. So it's a really good navigation tool that we used to use a lot when we were talking about projects and orientation. All right, so here is a beginning a use of even just a presentation tool to your staff or whatever, talking about a preservation project and where problems are occurring. And then there's also two faint green lines that show you the extent of the field of view. So if I were to zoom out, and the points will load, but you'll see those, they're hard to see on the screen, but the field of view lines change and the direction changes as I move. All right, and you can create, we've done this on multi-story buildings when we're doing a conservation project where we'll scan each floor, put it all together, and then what I can create this site map for every floor. So I have a directional tool and I can basically dissect the building very easily, and then I can also add in other documentation like my thermography images or my photogrammetry, and I can geotag in all my external images, all my external reports, and basically use this database as an organization tool similar to a GIS system as an informational tool that we use as we're in the office to access information. All right, so this is just sort of scraping the surface in terms of how we use this technology. Okay, this was a scan that we did of the breeding barn at Shelburne Farms a few years ago in 2006, and I did it with Elizabeth and a group of students. And we basically did it, we did end up creating HABS drawings from the drawings, but this building was the breeding barn of the Vanderbilt estate, and it was a huge structure. It's 300 feet long. It's more elaborate than most buildings I've been in. It's just absolutely fantastic. If you ever get a chance, it's a gorgeous site and area to see. But basically what we did was they were having problems with the roof structure and a lot of the wood trusses, the King and Queen Anne post trusses and whatnot. And so what happened was the engineers and architects wanted some information about the deflection and the snow load of the roof capacity. So we went in to scan it on with sort of two purposes in mind. One, to create HABS drawing, and one, to use the scan data for structural analysis, not to analyze the materials, but to basically draw hundreds of measurements to give them some information to validate their calculations. So this is just showing you some information of the overall scan. This scan was done with an older scanner, and so the data is not quite as crisp and clean as some of the new scans that are coming out today in this technology. So in 3 years, it's greatly improved. This just shows some basic measurements that we were able to you can quickly draw those type of measurements and get heights and whatnot. And I didn't include all of our structural analysis, but that's just gives you an idea of the interior and some of our measurements. And then this is just this just shows you one of our sheets of drawings for the HABS projects that we got from the scan data. This was an interesting project that we worked on. Dr. Loudon and I worked on this project, and they were down in Victoria, Texas, at Our Lady of Lourdes. The plaster craftsman needed to replicate an altar, and so we were instructed to go in and scan it. And basically, they used the scan data to create what we call a tin model. And what a tin is it's a triangular irregular network where they connect the points to create a surface. And then what they did with that is they reverse engineer, they use a 3D printer to create a model of the certain parts from the scan data, and then they create molds from that, and they're able to cast all the small pieces to fit together to build the altar. And then what they did was they went in and then added the fine-tuned details on the carving, but they got the overall massing by piecing it all together. When we scanned this, we used a different kind of scanner called a phase-based scanner, which is basically a close-range scanner, and the accuracy on that close-range scanner is approximately 2 millimeters. So we were actually able to tighten that up by when we register, which is the process of putting different scan information together, basically putting the puzzle pieces together. When we registered the data together, we were able to get that down to 1 millimeter. The accuracy on this scanner here is 4 millimeters because the width of the beam coming out of that instrument is exactly 4 millimeters. We can tighten that up again through the registration process, because as the scanner works relative to its position, you're never going to get the same exact point. So when I scan that wall from over there and then I scan it from over here, the points are never going to be the same because it's a swath of points. And when I register those together, I can get a tighter resolution by overlapping data. Okay, now this is I've just included this as an example to show you what you can do with scan data. This is just a data set I use in training a lot when I'm teaching people how to model from scan data. This is just a simple scan of a railway bridge, and then what you can do is that you can actually use the point cloud data to create a model. Okay, so none of that all that is generated from the point cloud. All right, so just showing you part of the model of the point cloud. And to be able to model that from the point cloud, all of that detail took me probably about 6 to 7 hours. Okay, so it's labor intensive if you're going to take it to the modeling aspect. But again, a lot of the times we don't ever take it to that detail. And the nice thing is once you have a model built and you spend the time to model the point cloud, you can slice and dice the model any which way, and you have component parts and sections through it. You can also obviously section and cross-section the point cloud, and you'll see that with the students' drawings, how they got their section drawings from the point cloud. And again, you can also extract 2D drawings from a modeled surface. You can't, right now the technology isn't where you can scan a surface, press a magic button, and extract a 2D drawing from the point cloud, but it's pretty close. That technology of getting a really good 2D extraction from a point cloud is very fast approaching in terms of its accuracy. So we're going to, I think over the next few years, you're going to have that magic button, and we've been waiting for it for a long time. So from the engineering aspect, again, this is just showing you some other applications in engineering that we use the point cloud for. So if you want to just quickly read through that list, I don't want to read through it, but I wanted to point out that due to the large scale and complexity of these projects, the scanner provides an efficient way to conduct these, to basically document these resources in situ. Early scanning applications were really designed for the oil and gas industry. So scanning started, and the need for scanning started out with scanning industrial plants and whatnot, and I'll explain that a little bit further in a second. So, and the technology is so adaptable that it's ideal for these large structures. It's a great way to scan these electrical poles and things of mass scale. Also, another thing to think is survey data can be integrated into the point cloud to tie it to other data sets or georeference it. So surveyors are out there setting up over a known benchmark or a known control point with a control point that ties into real world coordinates, and the scan data and the total station can all be integrated, either using total station or GPS. Okay, and this is an example of a deliverable that we typically do with scan data. So we went out and scanned this roadway intersection, and then we are able to basically pull a CAD drawing off of the scan data. So in that reference, we have available on the market from a variety of different sources plugins that go into AutoCAD, 3D Studio Max, Revit, Maya, and whatnot. So you're able to take that point cloud into these programs and use the drafting capabilities within those programs to create very fast and very accurate deliverables. I mean, the drafting on that to produce that drawing is about 2 hours in CAD off the point cloud with the plugin. So a lot of engineering firms are doing that to produce really fast, reliable surveys for their companies. Another interesting thing is I just included this scan of an aircraft because we get a lot of engineers from Boeing coming through training and whatnot, so they're using, they scan all of their modules when they're building them and use that information for crush, for development, for strength, and all kinds of different applications. Also, Homeland Security is scanning all of their airports and all of their different kind of areas for protection, and actually also for strategic planning as well. And I'll talk a little bit more about that when I get into another field. And this leads right into forensics. So I have to say that forensics is a very fast-growing market across the world with scanning, because the nice thing is it captures the information when the crime happens or when the crash happens. So it's really becoming very widespread. And again, these are some of the deliverables that the police and law enforcement are actually executing and taking to court. And it's actually gone to court, and there's been no, to date now, there's been no problems with it taking it to court, and there's been no appeals on the status and the verification of the data. This just shows you an example of something that we can pull for forensics out of the scan data. We can, if there's a shooting, we can put in a rod that maps the trajectory of that shooting, and we can take what we call the cone of variation. There's a 5-degree cone of variation based on that trajectory of the shooting, or the bullet trajectory, and we can map those trajectory rods and all bring them back to the point where the shooter was. We can isolate skid marks for traffic accidents and all kinds of calculations in terms of pitch and what happens, and the traffic reconstructionists are able to create 3D models, not necessarily animations because we don't want to subject any kind of false information into it, but they can basically take the point cloud as a raw piece of information and put in moving cars to show the acceleration, and based on measurements from the point cloud prove what happened during certain incidences. Okay, another really important field for scanning is studying the landscape and the natural environment, because scanning is a great tool for being able to measure this. This is a very difficult sort of environment to measure in based on the complexity of the natural landscape. And so there's a lot of interest out there for instance, the Washington State University is doing a very interesting study right now where they're integrating airborne lidar and terrestrial lidar, and they're able to actually calculate volumes of different types of tree species based on the scan information. So a lot of people are writing their PhD and writing actually separate scripts and code to be able to take that raw data and base those calculations on the information. So we're going to see some pretty exciting stuff come out of there in the next couple of years based on that. But again, even from a cultural landscape or even from a historic building preservation, an interesting project that we worked on is we went out, TxDOT was moving one of their historic bridges for a hike and bike trail just to preserve the bridge. We went out and scanned the historic bridge in situ, we modeled it, and then we went and scanned the new site where the bridge was going to be placed. And what we were able to do in the CAD environment through the point cloud is we were able to insert the model of the historic bridge in the point cloud of the new site, and we were able to help the engineers calculate the approaches and actually get a better fit in situ of where that bridge was going to take place. Another interesting application is viewscape analysis. What we've done a lot is gone out and scanned areas from historic districts. Good examples down near the border. They're often putting in those flyovers for the border safety inspection facility. So we'll go and scan from the historic district, from many spots in the historic district, and then put in the CAD model of the new flyover or the border safety inspection, and actually take viewscape analysis to see the impact on that historic district. So that's just giving you some creative applications of how we've used it in the past years to validate and actually put it to good use. Scanning is excellent for volume calculations. Something you may not think of is the construction companies that are moving gypsum piles or rock piles or anything that has, you know, sand for construction. So there's people actually that have jobs and all they do all day long is scan piles and do quantity takeoffs for construction companies. So it's a very easy thing to do with the scan data. Another thing I wanted to mention was plant. Plant and industry is one of probably the leading applications of scan data, and it has to do with the fact that you don't have to get 100% coverage in a plant to be able to use the information in a useful way. If you're on an oil rig or in a nuclear plant, all you need is approximately 20% coverage to be able to model the pipes or the fittings that you need, the valves or whatnot. So again, here are some applications. This is a picture of a cherry plant in Washington State, and we scan this cherry packing plant because in their applications from day to day, they're always moving their assembly lines around for different productions of different fruit during the different times of year. And so they want to maximize how production can occur. So they're using the scan data, and we modeled it, and we're able to move the parts around to improve their productivity in terms of their assembly configurations. Here's an example of a plant scan, rather comprehensive, but again, that's not a lot of scanning. It's what you do with that information. So what you can do in the software, different software products out there that will handle point cloud, is you can begin to model in pipes very easily, and this is where the 20% coverage comes in. You can model in pipe racks, and actually you only really need to model in what you need in order to make adjustments and changes. So what happens is they often go in and do a scan, and the green up there shows the insertion of new pipe configurations, so that they can use that for clash detection. So often a good thing to know is it goes through a cyclical process, but it happens with the oil rigs or oil platforms as well as the nuclear plants. They shut them down every year and a half to 2 years, depending on their cycle, and they'll send teams of scan crews in to scan for a month, and then they have their data set, and they use that data set for clash detection and also assembling new parts on the rig. So it's a really fast way, and mostly when those parts are modeled, they're all geotagged with the part number and everything, and they're able to insert and basically retrofit all of the new design in situ in their 3D model on their laptop. So I just gave you kind of a really brief overview of what's really capable. And I'm just going to end with this really neat video that shows a deliverable done through a movie that's fairly easy to put together. And this was done by Plowman Craven this project existed in Ireland, and it's kind of a really interesting overview of some of what I just briefly talked about. There's no sound, so. Yeah. And again, all of this was done from the scan data, and it starts off and it'll show you how the scan data integrates into these drawings. Again, using the plugins via CAD and being able to bring the point cloud into CAD and draw straight from the point cloud.
All the bridges along the river.
Mm-hmm. The 109 that they surveyed, yeah. And then they'll go into one specifically, and you'll see the scans and the information from one of the bridges. What's that? Yeah, it's a bit of an advertisement, but it's kind of, it has a really good overview, and that's why I included it, and you'll see why in a second. So that's the raw scan data. That's what raw scan data looks like. So all the different color variations is based on the reflectivity of the surface. And you'll see that of your room scan shortly.
What method of scanning was this? Was this a LiDAR? Or?
Yeah, this is terrestrial LiDAR.
Terrestrial.
Yeah, and you'll see that in a second. Yeah. So what they've done with the scan data is they're building up the walls and the edges of the bridge the scan data was used to create those models, and that's what we call a TIN, triangular regular network. And to get that uniformity over the point cloud, what they do is they create what we call an irregular TIN. So they create a surface from the point cloud data, and then what you can do on that surface is you can drape a regular TIN on top of it, meaning that you can decide what the spacing is between the points. So you determine the surface from the original scan data, and to get a good look at the data, to get a good looking tin like you saw just a few minutes ago, you drape a regular tin directly on top of the irregular tin to make it look nice. Not necessary, but obviously for advertising purposes and whatnot. And then what would happen is that model would be taken into 3D Studio Max or Maya in order to put those surfaces on there. And then just shortly, it'll show you the scanners that were used. It was both two types of terrestrial scanners were used for this project. It was an older version of this scanner called the 3000 that we've talked about, and also a phase-based scanner. And they also surveyed using GPS to georeference the scan data. So when that map fly in, and I know it was a little bit redundant showing you all those bridges, but all those bridges are georeferenced, so you saw them located in real space, and that's the phase-based scanner. So it's a closer range, so that's within 2 millimeters. And the one on the left there, and that's a total station, the one on the left is the 3000. Okay, so now what I'm going to do is I'm just going to quickly show you a copy of what we achieved from the scanner. And what we're able to do with the scanner is we're able to actually run the scanner remotely. So I can run the scanner with any wireless device. I can run it off my iPad, my Android, I can even run it off my iPhone. So you probably know this, but most computers come with a remote desktop application. So I can use my laptop like I can my iPad. So I can actually connect into that scanner via my wireless network, and it's not related to the internet, it's just related to the wireless. So what I have to do is I have to go into my wireless settings, which always takes my machine a little bit. I apologize for this coming up. It'll take a second for my menu to pop up.
Because we didn't tell the students they could run it from that iPhone.
Yeah.
We wanted to make them do it the hard way. The 3000, we'll just say quickly what you're doing it. The 3000 requires a direct connection, a crosstalk cable linked to your laptop, and a direct power source. The new one that we have, the C10, has onboard batteries, and it can be done wirelessly or an onboard control that you saw Eric go up and just start it right there on the scanner head. Where like the 3000, we had to be linked and tied, and so we were always dragging cables and cords and power cords everywhere. So it's a lot easier and quicker to set up.
So what I do here is I go into my wireless settings and I go find, and you'll find whatever scanner you're running on the wireless network. So there's the serial number of that scanner. So I double click on the scanner and I connect to it wirelessly, and that allows me to use my remote access from whatever device I'm using. So as soon as this connects, And again, you can see where this has some great applications. If you're scanning from a rooftop or whatever, you can set the scanner up there and then, you know, basically go down to the ground and scan from a more reasonable position. So on a laptop, what I have to do is go into my accessories menu and go into my remote desktop connection. So go into my remote desktop connection. And basically, you just need a little bit of information. You basically need to know what the IP address of the machine is you're remoting into. You hit connect, it'll connect to it. And then in a second, I'll see the main scanner screen come up here. It just takes a second to initialize. Part of the slowness too is being connected to a projector. The password is the sensor board control. Okay, so basically what this shows you is a panoramic layout of the scan. And so what I can do, and I know it's not very big, but what I can do is I can zoom in and have a look. And I don't know that we got a full dome scan on this one, but that's okay. But this is the intensity map of the scan. So basically what I'm seeing here is if I zoom in, I can see all of you sitting in the audience. Now this is going to look very different when I download it into the software, but it takes a few minutes, so I didn't want to obviously do that on a demo, but this is the intensity map. And again, it's captured you in real time, and it's just a preview of what the scan data is going to look like when I import it in. All right, and on this little remote, I'm not able to show the colors from scanner. One, I didn't take a photograph, but if I had taken a photograph, I have to actually import that into the software to be able to see those nice colors on the scan data. All right, but what we're able to do from here is again do high-res scans and continue. All right.
I think that's Lisa's spin.
Oh, okay. So anyways, I just wanted to give you a really quick, really quick brushstroke overview of scanning. There's certainly a lot more and a lot more complexity to it, but there's really some exciting stuff being integrated with photogrammetry, thermography, ground penetrating radar, geotags, GIS, airborne, terrestrial. They're all integratable based on GPS and survey points. So with that, I'll conclude and pass the floor back over to Elizabeth.
My goodness, we ran way over. So I'm going to let you run, unless you really have a pressing question. Okay, I didn't think so. Okay, so thank you all for coming again. Again, we appreciate all of our speakers, Dean Vernoy's support, all of our guests that have come today, and the distances they are now having to return to go home. Safe travels, everyone, and we'll be in touch.